Next, we consider two-body phase space. In the previous class, we studied the invariant mass of two-particle system with rest mass m1 and m2, whose four momenta are given by p1 and p2. Invariant mass of the two-body was just capital P squared, where capital P is the sum of the two momenta. And when I squared this, this was capital M squared, that is invariant mass of the system. And actually there is E squared minus P squared, vector squared, or E1 plus E2 squared subtracted by P1 vector plus P2 vector squared. In the center of momentum frame, where the three momenta, sum of the three momenta for the two particle becomes 0, and in that case it is reduced to be the energy of the two particles squared. So the invariant mass of the two-body system is the sum of the two energies of the particles at the CM frame. Okay? So using this fact, we can consider a decay of a particle A, whose rest mass is capital M, into two particles with a mass m1 and m2. The decay of a particle is possible in relativity in case capital M is greater than m1 plus m2. It's possible to have equal sign only if the energy mass of the decaying particle is greater than the sum of the two masses of the daughter particle. It can decay into two particles. Okay, and if a particle with capital M is decaying into two particles, it acquires the kinetic energy. So sum of the two energies that is greater than, always greater than the sum of the two masses of the particles. That's the reason why the capital M must be greater than the sum of the two masses. If the equality is valid, then there is no kinetic energy. That means that this particle M1 plus M2, capital M is the sum of the two particles, and then it decays into two particles and they do not move. So they are at rest. That is the threshold, the minimum value of the capital M decaying into two particles. And if the mass of capital M is greater than M1 plus M2, then the two particles can move. In the center of mass frame, the sum of the two momenta must be 0, and because the initial particle was at rest, so sum of the momenta for the final state must be the same as the initial state. So if this particle is moving with this momentum p, then the other particle must move with momentum minus p, so that the sum of the two momenta is exactly 0. So it's always good to make use of the center momentum space, center momentum frame. In the center momentum frame, capital P, the total momentum, or the mother particle's momentum, is capital M, rest mass of the particle, and 0. In the center momentum frame, two momenta for the particle 1 and 2, they are opposite and equal, P and minus P. And they have energy E1 and E2. Sure, the E1 and E2 is the square root of M1 squared plus P squared, and E2 equals square root M2 squared plus P squared. In the previous class, I used the star, just like this, but from now on we will use the CM frame frequently, so I just remove the star. Alright, so the constraint of the sum of the momentum is 0, does not say the direction of this momentum is fixed. So this means that this momentum P of particle 1 and minus P for particle 2 has arbitrary direction. There's no constraint. So if I write it down, the vector, and along the z direction, and m is at rest, then the momentum P can make an angle theta. There's a polar angle theta with respect to z-axis. And it is a three-dimensional space, so z is here, x and y axis. So there is azimuthal angle possibility. So theta can change from 0 to pi, and phi can change from 0 to 2 pi. So we have allowed region for the angles. In the previous class, we have solved the equation for the constraint to find the energy of the particle 1 and particle 2 are given like that. Where capital M is the mass of the matter particle, and this is M1 and M2. You have the different sign, plus for the particle, the same particle identity, and minus for the other particle. All right? So we have a squared in the numerator, the linear term in the denominator, so the scale is mass. The energy of the particle 2 has the same formula, except that 1 and 2 are flipped. So if we exchange, replace 1 by 2 and 2 by 1, then we get the same and similar formula. And another important result that we obtained in previous class was the magnitude of the momentum in the central momentum frame for a single particle, 1 or 2. The magnitude is the same, the minus p and plus p, so magnitude is the same. It's just a 1 over 2m. In the previous class, I made a mistake. Capital M must be 1/2. Capital M, lambda 1/2, 1, m1 squared over capital M squared, m2 squared over capital M squared. But in this formula, I must use m in the numerator instead of the denominator. This is the correction. Okay, so this function can be expressed as this kind of form. All right? So if I make use of this polar angle, azimuthal angle, then the forward momentum of a particle 1 and particle 2 and capital P at the center of momentum frame is expressed as energy and momentum. Polar angle is theta along the z direction, so this cosine theta. And x component and y components are sine theta cosine phi, sine theta sine phi. And because the P1 and P2 has a vanishing sum for the three vectors, I have the same magnitude but opposite direction. Okay? So, let us consider the possible values for the three momenta of the finite particles. Our constraint is that the two particles are opposite and each particle has mass shell condition. That means energy squared subtracted by momentum squared is always satisfying m squared. So I'd like to know what are the possible values. It is in an abstract way we have described a lot of regions for the final state momenta for P1 and P2, but this is the way how to construct a phase space. Phase space is the allowed values for the momenta for the final states. Okay. So two-body phase space is summarized to be allowed angles are angle theta is running from 0 to pi, azimuthal angle is running from 0 to 2 pi, and allowed momentum is the magnitude of momentum is clearly fixed if the initial mass and final particle mass are fixed, that they are completely determined, and the function lambda is defined like that. We have another constraint that each particle has on their mass shell. That means energy squared subtracted by momentum squared is rest mass squared. So P1 squared equals M1 squared, and P2 squared M2 squared, capital P squared M squared. And we have energy momentum conservation in initial mass is the same as the sum of the final energies, and initial 3 momentum is the same as the sum of the final state 3 momentum. Before we go ahead, we just make use of a simple relation. All right. When we learn particle quantum mechanics, so we have integrated over the x exponential IPX, integrate over minus infinity to infinity was defined 2 pi Dirac delta function of p, right? If we generalize this one into 4-dimensional space, IPX is IP dot x is IP0x0 e to the minus IP1x1 e to the minus IP2x2 and e to the minus IP3x3. So this exponential can be integrated over the 4-dimensional space. So if we integrate over the 4 dimension, each integral, x0 integral, x1 integral, x2 and x3, all 4 integrals generate the 4 pi delta function. So this is 4 pi delta 2 pi delta P0, 2 pi delta P1, 2 pi delta P2, and 2 pi delta P3. So we have 2 pi to the 4th power and 4-dimensional delta function. We call these the product of 4 delta functions is defined to be delta 4p. And if you look at the right-hand side, it is not clear whether it is a Lorentz invariant or not. However, this p dot x is already a Lorentz invariant quantity, and we learned that the 4-dimensional integral measure is a Lorentz invariant again. All right, so actually this 2 pi 4th power delta function, capital P minus P1 minus P2, I just replaced this small p by capital P minus P1 minus P2. This means that this value is always 0. So the requirement that energy momentum conservation between the initial and final state can be written as just delta function and integrated over all possible P1 and P2 regardless of components. That means if we can integrate over P1 dP1 dP2 to the 4th power, okay? If I integrate this function, then it is the answer is we require P equals P1 plus P2 always. Another requirement must be implemented that each particle has this equal mass. That means, and again, each particle has a positive energy. There is no particle whose energy is negative. Nobody has found a negative energy particle. So this is the way how to implement that. So if we introduce a delta function, it is conventional to introduce the 2 pi for each delta function. So let me just put 2 pi. And this is a delta function that keeps the P1 squared to be always M1 squared. And another requirement that energy of the particle is a positive means that P1 0 component must be +1 for positive value, 0 for negative value. Theta is a function, theta is a step function that theta x equals 1 or 0, 1 when x is greater than 0 and this is less than 0. And because there are 2 particles, I have this vector for the particle 1 and particle 2. Okay, the first line is energy momentum conservation, and the second line is for the unshelled condition for two final state particles. Now we integrate over all possible values for P1 and P2. Okay, so here we have fixed all the values and we consider only physical values, but here collection of the physical value is automatic by multiplying the delta functions, and we just integrate over all possible, even including unphysical case. Then these delta functions will kill any component, any contribution that is unphysical and keeps the physical quantity only. So we now integrate over all possible final state, including unphysical space. So that means integrate over minus infinity to infinity for each component of P1. That means P10, P11, P12, P13, and P20, P21, P22, P23. So that can be done, but in conventional ways, p to the fourth power 2 pi 2 pi 4th power, and p to integrate over p2, multiplying the over factor 2 pi in the denominator for each dimension. So this is a definition of the two-body phase space. Okay, d phi 2 means the two-body phase space. That is, I have energy momentum conservation. 2 pi to the fourth power is coming from the fact that we have 4 delta functions. 2 pi to the fourth power, and we have delta function, 4-dimensional delta function, that energy of the initial and final states is the same, and each component of a 3 momentum must be the same between this initial and final state. The next one is the unsure condition for the particle 1, unsure condition for particle 2, and positiveness of the energy of those particles. And I had 2 pi for the delta function. I had to the fourth power of 2 pi in the phase space integral. I have canceled the 2 pi from the delta function and the denominator. So if we combine, okay, before we go ahead, we just consider this factor. Did we talk about the Lorentz invariance of this second factor? This is whether this is delta function or not. The argument is just the p1 squared m1 squared, p2 squared m2 squared. So this delta, 2 delta functions are Lorentz invariant because the argument itself is expressed as Lorentz invariant quantity. But what about the theta function? Theta function is also Lorentz invariant. Why? A particle with mass m, a positive mass particle, if it boosts, zeroth component always increases and never decreases. So if it were positive, then it is always positive, regardless of the frame. In case it is negative, the negative value will boost to more negative value. So they are symmetric and they never cross the border. No Lorentz boost from the rest frame make the positive sign, positive mass particle to have negative energy. So the constraint that we have positive energy, then it is always a positive in any frame. You can show it explicitly. So this whole factor is Lorentz invariant. And this delta function was shown to be Lorentz invariant too. So this phase space is Lorentz invariant. That is good, because if it is Lorentz invariant, you can evaluate this phase space in any reference frame, okay? In any inertial reference frame. So let us consider this second factor, the mass condition, unsure condition. We have 4-dimensional integral over the P1, and we have P1 squared minus M1 squared in the delta function, and we have theta function that the energy of the particle is positive. We can separate the 4-dimensional measure into spatial measure and the zeroth component. Perhaps we, okay. And if we rewrite this by component, then it is P10 component squared subtract by P1 vector squared. And we have mass squared here. I have combined the mass squared and 3 momenta. Right? And now it is factorized into the P10 plus the square root energy of the particle. This is the energy of the particle. And I have negative sign here. This is a delta function. Argument is a product of two functions depending on P0. I have P10. This is P10. So this function, this argument has two zeros when P1 is minus energy and when P1 is a plus energy, right? And this delta function can be divided into two pieces when this guy has a 0 and when this guy has 0. When this guy has 0, I have vector minus 2 energy, and absolute value of the minus 2 energy is 2 times energy in the denominator. Okay? And I have this guy, so this 0 is replaced by a simple delta function, and over vector becomes P10 is replaced by this one. So 2 times energy is in the denominator. Now we can integrate out this P10 by using theta function. This theta function requires that P10 is always positive. Because if this is always positive, this theta function never becomes non-zero value. It is always vanishing. So only this guy survives. So as a result, it is simplified as the three-dimensional spatial integral for the momentum, and P10 is integrated out. Oh, I missed the P10. After integrating all over P10, this delta function becomes just 1, and this is replaced by 2 times energy, where energy is the square root of P1 squared plus M1 squared. So in the same way, I can replace the second factor in the same way. I have D3 P2 and 2 times E2. So if I substitute these factors into these expressions, what I get is I have 2 pi 4 coming from the energy momentum delta function, and minus 6, 3 by 3, 2 times 3, minus 6, and then 4-dimensional energy momentum delta function, and P1 and P2 has 3-dimensional integral. If you look at this delta function, this delta function is composed of 4 components, right? 0 component, the energy, and 3-dimensional momentum. But there is a P2 here. This P2 can be integrated out by using 3-dimensional delta function. Okay? That means if you integrate, after you integrate, you find that P2 is capital P subtracted by P1. You can obtain this kind of constraint by integrating over this delta function. After you integrate over this delta function, what you find is just only the energy part. That means capital P0 subtracted by P10 minus P20. Okay? That I have replaced by E minus E1 minus E2. And in the denominator, I have this 2 times energy of the first particle, 2 times energy of the second particle. Okay? So this is a Lorentz invariant. That's important. So because this is Lorentz invariant, we can evaluate this integral everywhere. And that is the same, that has the same value. The most simplest frame where this expression becomes most compact is what frame? Center momentum frame. In the next page, we will simplify this in the center of momentum frame and parameterize this the two-body phase space in a simplest way. That's it.